Here's the thing, like a lot of this lesson that we started yesterday is review, right? Kind of taking some of the concepts that we've looked at and applying them. So example numero tres. Limited infinity, right? So as soon as you see the infinity questions, we're thinking about the last lesson, right? We're thinking about what happens at the extremes. We're thinking about, is the numerator larger than the denominator in terms of that chart, right? Well, not that chart, but that progression of constant to logs to power functions to exponentials, etc., right? We're thinking about, what does the graph look like? We're thinking about horizontal or slant asymptotes, right? So these are all the thoughts that are sort of going through our mind. So what do I notice about example 3a? Well, I have a numerator and a denominator, right? And is it fair to say that they're both power functions? Right? When I say power functions, what am I talking about? I'm talking about variables with powers on them, right? Well, when I have this scenario, I typically will look and see if what? The degree. Okay, so I heard factorable. True. Sometimes we'll factor, right? But I just want to know about what's happening in infinity. So in that case, I'm not looking at a particular point, so factoring is really not going to help me. So what would you say about the degree of the numerator and denominator? They're the same. If the degrees are the same, what does that tell me about my graph? It has a horizontal asymptote where? At y equals negative 5/4. So what's the limit? It's negative 5/4. All right, the next one. I got no idea what this graph looks like, right? I have no idea what this graph looks like, but I know what that looks like. What's that? Well, it's the graph of natural log, isn't it? Or log, either one. What do you guys notice about the value of everything in a natural log curve? All the x's are what? Positive. They're all greater than 0. So here's the issue. This problem says that I want to evaluate the limit at negative infinity. Can I plug negative infinity? Can I plug it in? Well, I can plug it in. And there are times when plugging it in is going to create something that is non-existent, right? Can't do it. Well, if I plug in negative infinity here, what am I doing to it? I'm taking an absolute value, which is going to make it positive infinity, right? So where am I going as I go to positive? As I plug in negative infinity, I'm moving more and more to the right on this graph. So where is this going? It's going to positive infinity, or does not exist. Piecewise functions. Okay? When we look at piecewise functions, we're typically determining if our function has a limit at that value or not. Guys, when does something have a limit? When they come together, which means the limit from the left is the same as the limit from the, okay. So in this case right now, if I want to know the limit at 2, I really want to know, is the limit as I go from the left equal of f of x? Is it equal to the limit as I go to 2 from the right? That's the question. If the answer is yes, then the limit at 2 is whatever I get. Otherwise, it doesn't exist. So if I plug in a number a little less than 2, which rule am I within? I'm within the first one, right? So if we plug in 2, what do we get? 1. All right. If we plug in a number a little bigger than 2, we're within which rule now? Second rule. We plug in 2, what do we get? Half of 2 is 1 plus 1 is. So what do I know about the limit at 2? Does not exist. Because why? The limit from the left and the limit from the right did not meet, right? Wrote in, wrote out, not at the same spot. Okay? At pi, does the limit exist at pi? Well, the limit exists at pi if the limit from the left of pi is equal to the limit from the right of pi. So if I'm to the left of pi, then x doesn't equal pi, right? So that means I'm over here. I'm in this rule for both of them, right? So let's take a look at sine. Well, we all know that sine looks like this. And this is our value of pi. Well, let me ask you this, guys. If I get on this thing and I approach from the left, what value am I nearing? What value of y am I nearing? 0. Okay, if I approach from the right, what value of y am I reaching or approaching? 0. So the limit from the left is 0 and the limit from the right is 0. So the limit of this function at pi is 0 because they're the same. Cool? All right. Then we talked about squeeze theorem. And guys, I don't know what some of these sayings are. But how do we know we have a squeeze theorem problem? Well, we have a what? We have a left side. We have a right side. We have a middle, and then we have that inequality, right? So we have something that fits within two different functions, okay? And it says that this function for all x within this interval containing x equals 1, except possibly at x equals 1, find the limit at j of x. Okay, well, let's take a look at what we're going to do. You guys all agree I'm going to take the limit of each of these pieces at what value? At 1, all right? Is there anything to actually do like we did within the actual examples of the squeeze theorem? Within the actual examples, what did we try to do? We tried to match the inside, and we did some manipulation of the entire thing, right? Here they just say there's some function j of x that's squeezed between here and here. Can I figure out the limit? Well, I can figure out the limit if what? If this and this happen to be the same, right? If these happen to be the same, then this has to fit in the middle of it. And we saw that graphically, didn't we? Okay, so let's take the limit of each of these pieces. Quick question. Easiest way to find a limit? Plug it in. Are there cases when I can't? Of course. We've looked at a million of them, right? Asymptotic functions, functions with holes, right? Non-continuous, all those examples. All right, but if I plug it in, what do we get? Well, we get the natural log of 1 plus 1 squared. Is that less than or equal to? Is that equal to that? And this is where, without a calculator, I get that sometimes we have some troubles. The natural log of 1. The natural log of, why is it doing this? The natural log of 1. Guys, what's that the same as? That's the same as log base e of 1. So if I want to know what that's equal to, I could say it's equal to x. So how do you convert this to an exponential? E to the x equals 1. So what power would x have to be for this to equal 1? It would have to be 0, right? Okay, so x would have to be 0, right? So this is equal to 0 plus 1. And this is equal to e to the 0. And what's anything to the 0 power? It's 1. So did it squeeze? It did, right? So the limit of j of x has to be 1. And there's our justification, right? All right, so these are all things that we've done, okay? We're going to look at a couple of things in a few minutes that are like, kind of like, what? Picardo, I mean, we didn't do that. We'll see some of those in a few minutes, okay? Can I find limits of these? Well, this was like what we started with, isn't it? And you said you want a factor. Agreed. Because where am I finding limits? Am I finding limits right now, guys, at infinity? Oh, now I'm finding limits within ranges that are closer to 0, right? So if I plug in 0, is that a problem here? Come on, simple question, guys. If I plug 0 into this, is it a problem? It's not. We can plug 0 in. Oh, sorry. If I plug 2 in, is that a problem? Yes. Good. Why is it a problem? Because it would be undefined, right? So the question is, uh-oh, it's undefined. Now I got to decide what's there. Either a hole or a asymptote. Because if it's a vertical asymptote, does the limit exist? No. If the hole exists, I got to figure out where it's at. Agreed? Okay, so again, these are the thought processes that you need to be going through on Monday, right? I got to find a limit at this point. I know I can't plug 2 in, so what am I going to have to do? And now I'm going to factor and reduce. All right, it factors. It reduces. What does that mean? Hole at 2 comma what? 2 comma 4, right? 2 comma 4. So if there's a hole in my graph at 2 comma 4, that means that the limit as this graph approaches 2 is what? Is 4. It's the location of the hole. Quick question. Am I allowed to plug 1 in to this one? I'm allowed to plug it in, but is it going to work? What's going to happen? Either a hole or an asymptote, right? Do I know which one? I don't. Okay, so what do we need to do? Well, we got to factor it out, right? So my question is this, and we saw this yesterday, guys. If this divides evenly into this, what do I get as a remainder? 0. Agreed? If this divides evenly into this, I get a remainder of 0, don't I? The same way if this was a 3 and this was a 12, if it divides evenly into it, you get what? 4 with a remainder of nothing, right? Okay, so I'm going to try to see if it divides into it evenly. How am I going to try to do that? I'm going to use synthetic, right? And when we use synthetic, what did I put in the box? I put the root of the divisor. And what do I put here? I put the coefficients in order. So I have 1x cubed, I have no x squareds, I have no x's, and I have a negative 1. Down comes the 1. Now what? How do I do this? What do I do? Multiply, add, multiply, add, multiply, add. 1 times 1 is 1. Add these together and I get 1. 1 times 1 is 1. Add. 1 times 1 is 1. Add and I get 0. What does that tell me? It tells me that x minus 1 was a factor of that. So I know that I have an x minus 1 on top. Now, what was the result when I factored it? Well, it was this, right? How do you read this? This is 1 x squared. This is 1 x, and this is plus the constant, right? And that's the remainder. Okay. So, does this limit exist? Yes, it does, because there's a hole in the graph. Where's the hole? At 1, 3. So the limit is 3. All right. Now I got one of these, right? So again, guys, I know it's an overwhelming problem when we look at it like this, but we have to consider some ways to making it simpler. Can we factor the bottom? Do we have the ability to factor the bottom? We probably can. I know I'm going to have a 2x and an x. I know I have a 3 and a 1. I got to get a -1 in the middle. So I think the only way to do it is if that's a 3 and that's a 1 and that's a minus and that's a plus. What do you guys think? That seem okay? Yeah. All right, so here's my next problem. The only thing I'm concerned about right now, guys, is the limit at -1. So all I want to know is this gonna factor out with something on top? That's what I want to know. Do you guys agree with that? Because if it is, then it's a hole. And if it doesn't, then it's a vertical asymptote and the limit would not exist. So I'm going to do the same thing I did over here. I'm going to see if -1 will divide into this evenly, right? Using synthetic. The best case is if it doesn't, because then I can just say, done, right? Done, does not exist. And of course it does, right? So we have this skill from last year, and now we're seeing an application of where we might need it, right? So what do I know the top factors into? Well, I know it has an x plus 1. And then I know that it has this result down here, right? And how would I read this result? That's the constant, that's the x term, that's the x squared term, that's the x cubed term. So it'd be x plus 1 times x cubed minus 2x squared plus x minus 4. So I know that that factoring is correct. Now, Austin, is it possible that this could be factored more? It's possible, but do I care? I know that there's a hole in the graph at the factor of x plus 1 or at a point of x equals -1. So now the question is, where am I? Because there's a hole. Well, how do I get the y value? I take -1 and I plug it into everything else. -1 cubed. -1. -1 squared. Hang on, I'm just going to do it down here. -1 cubed minus 2 times -1 squared minus 1 minus 4 all over 2 times -1 minus 3. Now, if I asked you guys for the limit and it's a free response question, ta-da! There it is, right? There it is. I got it. That's where it is. You figure it out, right? If I actually had to figure it out, this would be order of operations time. This would be -1. This would be 1 times -2 minus 1 minus 4 over -2 minus 3. That all gives me -8 over -5, or 8/5. So a limit is 8/5, because that's the what? What did we just find right there? The y value of the whole. Yep, y value of the whole. You got it. Okay. Evan, bad news. You're hoping to get that 100 on Monday, so Evan sees this problem, and he says, Picardo said the easiest way to get a limit is to plug in 0. So he plugs in 0, gets radical 1 minus 1, which is 0, over 0, and it's undefined. And he's like, okay, well, if I plug in 0 and I get that, it must be a vertical asymptote, so it probably doesn't exist. But, like, what's all this stuff up here? And I'm not really plugging in 0. I'm really plugging in a number close to 0, right? So these are all the thoughts, right? So how do I handle this? Well, maybe I can, like, switch a whole bunch of stuff around where I can plug in 0 and get something that's a little bit more reasonable. What could I do to switch some things around? Well, rationalize by using a conjugate. So, what's the conjugate of radical x plus 1 minus 1? It's radical x plus 1 plus 1. What's the whole point of multiplying by a conjugate? To get rid of the radical, right? But when I do that, what's going to happen to the inners and the outers? They cancel, right? So I know I'm foiling the top. Guys, what's any radical times itself? What's underneath it? So I'm going to have the limit as x goes to 0 of x plus 1. Okay. Then I have this times this, that's the inner. Then I have this times this, that's the outer. Those are going to be opposites. And then I have -1 times 1, which is -1. All over x times, all over that. Now, what did I not do? Well, I didn't distribute the x, did I? Well, there's a reason why I didn't distribute the x. What's the 1 minus the 1 going to give me? 0. So now what's the only thing left on top? The x. And what's this thing here on the bottom? An x. So what do you think I can do? I can reduce this to be what? To be 1 over radical x plus 1 plus 1. Guys, what happens if I plug in 0 now? I get 1 over radical 1 plus 1, which is the same as, so I have 1/2. Right? You guys want to see what that looks like graphically? I have radical x plus 1 minus 1. Radical x plus 1 minus 1. And that was all over what? It was all over x. All right, so that's what it looks like graphically. And what was I curious about? I was curious about the limit at what point? I mean, what's crazy about this, guys? What's crazy is we just did all that work, and there was nothing even significant happening there. It was just a continuous graph, right? Add 0, I get a half. See it? Right? Okay, what about the next one? I plug in 3. What's the numerator? 0. I plug in 3 and I get radical 5 minus radical 5. 0, right? So can we do something to make it look a little nicer? We're going to try multiplying by the conjugate again. So this one, I got the radical on the bottom, right? But that's okay. We can still do the exact same thing. All right, so there's our multiplication by the conjugate on the numerator and the denominator. Again, guys, I stress certain things because I want you to remember them, right? I'm going to evaluate the denominator, okay? Because that's the thing that I'm hoping to clean up. So, what happens? Any radical by times itself is what's under it. The inners and the outers will always cancel. What's any radical times itself again? So this is going to be minus what? Minus 5. All right, and I'm going to leave the top exactly the way it was. What does the bottom become? X minus 3. What's on the top? X minus 3. Those are going to what? Cancel. Well, here's the thing. Even if it is a whole, what are you doing in the next step? Plugging in 3, which is the value of the whole. And where are you plugging in 3? Into what's remaining. So either way, it would do the same thing, right? You're still finding the limit at that point, right? So if I plugged in 3, what do I get? I get radical 5 plus radical 5. What's radical 5 plus radical 5? If you say radical 10, I'm going to throw my digital pencil at you. 2 radical 5. It's 2 radical 5, right? We starting to see why we did some of that prerequisite algebra, right? Starting to see a little bit. I mean, this is, you're seeing the concepts of limits. Bridge in, bridge out. Not hard, right? But when you start throwing all the algebra in there, within the same concept, right? I haven't changed the concept, have I? So we're starting to see how, like, again, calculus is not about calculus as much as it is algebra in the other classes. What time are we done? 06. Okay. Here's what I want to get. I want to make sure I can get through this, and all right. So I want to get through at least this piece here, and then we'll wrap up. I'll give you a few minutes at the end to get to take a look at some of the assignment. Okay. I'm going to rewrite this again, guys. I'm going to rewrite this so it looks a little prettier. All right. Where am I trying to find the limit? At 2? No. At 0. Why? What's the problem that we have? Plug in 0, and what do you get? You get a half minus a half over 0. You get 0 over 0. Bad, right? So our question is, well, how do we fix that? And that's why we reviewed this concept during the beginning of the year. What are my different denominators? I have a 2, I have a 1, I have a 2 minus x. The easiest way to get a common denominator is to take those 3 things and do what with them? How are you going to put them together? Multiply. Multiply. Absolutely. So I'm going to multiply everything by 2 times 2 plus x. Do I really have to write times 1? No? All right, so that's what I'm going to multiply by. Now that's really over 1. That's really over 1. So if I want to emphasize that, I can emphasize that. Austin, the whole point of doing this is so that when I distribute this to things, what happens? The denominator will reduce. Absolutely. So when I distribute this to the first term, what's going to go away? The 2 plus x. What's going to be left? 2 times 1. Okay. When I distribute this to the second term, what's going to reduce? The 2 and the 2. What's going to be left? 1 times 2 plus x. And when I distribute this to this, I'm not really distributing. It's just going to all be together. It's going to be 2 times x times 2 plus x. Now watch what happens. Evan, this minus sign gets distributed, right? So that's going to become 2 minus x. I get that. Now what happens? Now those x's reduce, don't they? What are we left with? We're left with negative 1 over 2 times 2 plus x. I want to go back. I want to make sure that that's clear because that was a lot of algebra. Guys, when I distribute this to this first term, the 2 plus x and the 2 plus x are going to reduce, right? Because the 2 plus x goes to the top and this is on the bottom. So all that's left is 1 times 2. That's where that came from. Minus. When I distribute this here, the 2's cancel. What's left? The 2 plus x. On the bottom, these just got multiplied together, so it's 2 times x times 2 plus x. This minus sign gets distributed. 2 minus 2 is 0. I'm left with the negative x. This is the denominator. The x's cancel. That's where that came from. Guys, if I plug in the 0 now for the limit, what do I get? Negative 1 over 2 times 2, which is negative 1/4. And that's the limit. Guys, try this one on your own. Same exact concept. One quick thing before you mess this up. This x on top, how can I rewrite that? X over 1, right? So my denominators are what? 1, 6, and x minus 6. Okay? There it is. Check your work. See what you did. Uh-oh. Evan's using his eraser. Mm-hmm. Right here. So do you agree that this is equal to 1? Why is it equal to 1? Because it's something divided by itself, right? Where did I get this from? Well, this denominator is 1, right? This denominator is 6. This denominator is x minus 6. So that's what I multiplied the top and the bottom by. Let me give you a simpler example, and then I'm going to come back to this. Suppose I said that I wanted to do this. And actually, this is probably not a simpler example, but math teacher joke. If I had this, suppose I had that, and I said that I want to evaluate this, and you don't have a calculator, right? What do? Well, if you go all the way back to learning fractions, my denominators are 2, 4, and 3. The least common denominator is the number that 2, 4, and 3 will all divide into. The easiest way to get a least common denominator is just to take 2, 4, and 3 and do what? Multiply. Now, when I do that, I get rid of the word least. It's no longer a least common denominator. It's now a common denominator. So 2 times 3 times 4 gives me 24, yes? So I'm multiplying everything by 2 times 3 times 4. Now, if I do it on the top and the bottom, it's really just multiplying by 1. Okay, so what happens now? What happens now is that 2, 3, and 4 all get distributed to each of these terms, right? So when I distribute 2, 3, and 4 to the first term, now what does it become? It becomes 1 times 2 times 3 times 4 over 2. This 1 was originally here, right? Plus 3 times 2 times 3 times 4 over 4. And then on the bottom, I had that 2 times 2 times 3 times 4 over 3. Now, if you do it right, what's going to happen? Guaranteed 100% of the time. That's going to cancel. That's going to cancel. And that's going to cancel. So what are all the denominators of all these fractions now? 1. So now, what do I have? I have 12, which is what? 1 times 3 plus 3 times 4 plus 18 over 16, which would give me 30 over 16 or 15/8. So there you have it, right? Now that's going all the way back to elementary school, okay? So how did that work right here? Well, I had a 1, a 6, and an x minus 6. So I multiplied all those together and distributed those to this, which is where that came from. When I distribute there to this, the 6 and the 6 cancels. What's left? 1 times the x minus 6, which is where that comes from. This distributes to this, so the x minus 6 and x minus 6, they cancel. What's left? 1 times 6, which is where that came from. And there you have it, right? And so yeah, it's a tough concept to see it like that, but then when you go back to elementary school version, it's like, oh yeah, okay, I get it now. Make sense? How we doing? All right, last bit of the day. Let's go. I'm going to skip over this. Make a note. We will do this later. All right, example 10. Guys, this is one of those concepts that people really, really, really hate, okay? They despise this concept. So you really got to like make sure you're with me on this, or it's not going to make any sense at all. I want to go back to your pre-calc class. And one of the things you guys did was decomposition of function. What is that? Absolute value, right? If I asked you guys to graph, let's call this g of x. If I asked you guys to graph that, what would it look like? Look like a V. No doubt. Okay, we know that. What if that absolute value sign wasn't there? How would this graph change? It would just be a what? It would just be a line. So this piece wouldn't be here. That piece would though, right? We all agree with that? Well, what does the absolute value sign do? It takes anything that was negative and makes it positive, which is why that part basically does what? Give me a word. Reflects. This piece reflects over the x-axis, doesn't it? So, can we all agree that a portion of this curve is reflected to create the absolute value? I'm going to rewrite this now. I'm going to rewrite this as a piecewise function. Because we all agree that there are two pieces. There were a piece that was reflected and a piece that wasn't. How do you reflect something in the x-axis? You make it negative. Okay? Give me the interval or inequality. Give me the inequality of the piece that was not reflected. Greater than 0. Give me the piece that was reflected. Less than or equal to 0. Now, guys, had Evan said this piece is greater than or equal to 0, then you would have said less than, right? Like one of these rules has to what? Equal. Like they probably both shouldn't though, right? That's kind of bad math, even though it would sort of work here. But it definitely, like you definitely can't have neither of them equal, can you? Because we all agree that this graph has a point that exists at 0, right? Okay, so good. All right, so I just created this piecewise function. Everybody comfortable with that? Okay. Now what I'm going to do is I'm going to take that concept and I'm going to take this function, right? And we're going to decompose this function. Okay? So now we have this new function. All right. So this was kind of like an aside, okay? This was an aside remark. All right, so let's do this problem. So now on this problem, we want to take this, right? And we want to decompose that. Well, guess what? We're just going to take the previous thing and apply it to this. In other words, this is the same as the piecewise function. Well, I have two rules, right? I have one rule for x and then one rule for negative x. So what I'm going to do is I'm going to say, okay, well, I have x over x, or I have negative x over x. What did I just do, guys? I took this and put an x on the bottom. I took this and put an x on the bottom because what? That's what it had me do, right? Now, what is this first rule? This first rule is when x is greater than 0. And what's the second rule? When x is less than or equal to 0. How are we doing? We're going to get to that. We're going to get to that. That's the perfect question to ask right now. Okay, so what are we trying to evaluate? We want to evaluate. Oh, we should do the other one. Hang on. It's saying, guys, that it's going to equal this, right? So if we wrote it the other way, or if we wrote it this way, then that would have been the same as that, right? So no difference within the two equations. You guys agree with that? The way they were written as piecewise functions. Still doing okay. All right, let's answer these questions. Well, actually, before we do that, what's x divided by x? Oh, thank you. What's x divided by negative x? Negative 1. So I have a function that is always 1 and always negative. So this is always 1 or negative 1? I mean, that's what this is suggesting, right? Let's see what it looks like. Look at that. Kind of cool, right? Kind of cool. Any questions with that so far? Okay. Now, what did I say would happen? Well, it appears that were I to flip this, I get the same thing. At least that's what it said, right? Let's make sure. Same thing, right? Okay. Let's go back to our notes for a second. Evan suggested greater than or equal to. Somebody over here said less than or equal to. I corrected some people. Talk to me about this function and these rules. If it's at 0, it's what? Undefined, right? So in most cases, when you create a new function like this, you have to consider all values of x, right? True? But within this particular example, we can't because it would create an undefined fraction. So we have to change that. If you wanted to do that, you could, but if you defined x equaling in here, then you've already killed that, right? You know what I mean? All right, let's quickly answer these. If I go to 0 from the left, x is what? Less than or greater than 0? Less than 0, right? So this has to equal x over negative x, which is the same as negative 1. What if I approach 0 from the right? If I approach 0 from the right, then it's going to be this rule, which is equal to positive 1. What if I actually hit 0? Does the road in and road out match? No, and we saw that visually, right? At 0, road in, road out. What would be on the ends of both of these? What kind of circles? Both of them empty, right? Good. All right, so this does not exist. And what happens at 3? Well, yeah, we're at 1, right? At 3, we're at 1. We're always at 1 if we're greater than 0, aren't we? Okay. Bye. Have a good night. So again, we're starting, I'm hoping that we're starting to see how all these tools that we've sort of put into play sort of come together, right? And we're seeing it now with a bunch of different examples, some of them rather easy, some of them a little bit more difficult, okay? So these are some of those weird cases that could happen, okay? And we're gonna continue to review these. So guys, you want to get started